Boa tarde a todos. É com a grande satisfação que a Sociedade Brasileira de Lógica, em conjunto com o Grupo de Interesse em Lógica da Sociedade Brasileira de Computação, dá início a esse seminário Lógicos em Quarentena. Muito obrigado, João Marcos, por ter aceitado o nosso convite, e obrigado a todos presentes. Então, estamos no horário, vamos dar início à apresentação do professor João Marcos, on classes of structures axiomatizable by universal de-Horn sentence and universal positive disjunctions. Se alguém tiver qualquer pergunta, pode usar o chat para ir se manifestando, que a gente vai fazer a fila para, no final, repassar as perguntas para o apresentador. João Marcos, muito obrigado.
Ok. Bruno, demais presentes, muito obrigado por terem vindo até aqui hoje. Essa é a primeira apresentação que eu faço inteiramente nu da cintura para baixo. Não espero ouvir risadas, não. I will now turn to English so that once this is recorded, this could be made available to a wider audience. So thank you very much again for the interest. The talk is going to be, as the title says, about something very long, classes of structures that may be axiomatized by certain kind of sentences. And those sentences are of two kinds in the title, the de-Horn sentences and positive disjunctions. I'm going to explain what I mean by this with some examples, but I first should let you guys know that this is already a paper published 2 years ago, which I think could get could arrive to a wider audience. That's why I propose to talk about it today. And it's co-authored by Guillermo Badia, who is now a professor at the University of Queensland in Australia. Now, I'm not a model theorist and not a universal algebraist, so why is it that I'm going to talk about this? Well, because I thought this was a kind of a subject that we could expand from the viewpoint of non-classical structures or non-standard structures, which are the kind of things which interest me a lot. So just to remind you of the well-known theorem about varieties from Birkhoff, which says that there are two ways of looking at varieties. One is by the definition of syntactical definition, in which you say that a variety is any class of structures that's axiomatizable by a collection of equations. I see it's AA, it should be only A. And the other thing which is easy to check is that, well, when it is axiomatized by a collection of equations, then it is closed under certain operations. So a class of structures with that property, you can easily check that it's closed under homomorphisms, subalgebras, direct products. But the other way around is the interesting result by Birkhoff, saying that, well, whenever you have a class of structures and all you know about it is that it's closed under these three operations, then there is a way of finding an axiomatization for these class of structures. A usual axiomatization by way of a collection of equations, so any such class of structures is a variety. Now, I'm going to mention a little bit of details about how the proof goes along the presentation, but at the moment it's really just worth noting that one of the main uses of the theorem is just one of the directions in which you want to prove that a class of structures does not have an axiomatization by a collection of equations, and then you do that by showing that it's not closed under one of these three operations: homomorphisms, subalgebras, or direct products. Now, it is surprising anyway that these two things coincide. And I now go to a paper by Tarski in which he makes a very interesting comment on these kind of results, in which he says that, well, our aim is here to work on what he called the borderline of algebra and mathematics by way of looking at mathematical notions, like the notion of axiomatizability by certain kinds of sentences, and trying to characterize this notion in what he called purely mathematical terms. And in this case, was through the closure under three operations that we have already mentioned. Now, this is a very bold aim And there are many ways in which it can be achieved. Also, you can go much beyond varieties in doing that. For instance, a beautiful result in the literature, which I do not aim to cover here, by Keisler and later on improved by Shelah, shows that the interpretations for first-order language are elementary equivalent, so they satisfy the same first-order sentences if and only if they have isomorphic ultrapowers. Now, this is a very interesting result, not only because what it says, but also the way it's proved. Actually, it was proved using what's nowadays called as Kreisel's trick, at least in the version by Shelah, as suggested by Keisler. And the proof is based on Gödel's consistency proof, and it actually involves the generalized continuum hypothesis. So it's a very powerful result, which goes much beyond equations. Now, there are other ways of going beyond equations, and what I want to talk in this presentation is about this industry, these ways of generalizing the Birkhoff's theorem. So I'm going to mention some of those and give examples from the next slide on. So theorem 0 is very well known, and the next theorems that I'm going to present in this talk are can be found in the paper that I have already mentioned, among other things. Now, the interesting thing about structures is that you do not need to restrict yourself when you're talking about mathematical structures to those which have equational specifications. And this is very well known. For instance, we certainly, all of us have worked at some moment with conditional equations, which are contain all the kind of things like an equation which is satisfied given a set of other equations. So it's like this set of equations implies the validity or the satisfaction of a certain equation. Now, this is one way of generalizing, and of course, this appears in several different areas. For instance, I will claim that in computer science, these things are very common. For instance, when you go into Horn sentences, which also are implications just like the conditional equations that I talked about, in which you have a number of premises implying a certain conclusion. Now, if Birkhoff's theorem talks about varieties, if you try to generalize it into taking conditional equations into account, not just equations, you have the so-called quasi-varieties. And if you want to talk about other things, like, for instance, what we will call universally negative equations, then you will have things like anti-varieties, which have also been studied in the literature by people like Gorbunov and his group, mostly, in recent years. But what I want to claim here is that, for instance, in the case of anti-varieties, which, when we talk about structures that belong to the same anti-varieties, it's easy to see from the viewpoint, for instance, of computer science, that they share the same constraint satisfaction problem, because these are problems about certain things not being the case. It's not possible to satisfy at the same time such and such and such properties. So this is a negative thing, which you cannot write in terms of equations. You need anti-equations to talk about them. But then when you go into Horn sentences, then it's even more clear to see, because if you look at this implication, the things on the left of the Horn sentences can be thought as being negative literals, and the thing on the right is a positive literals. And in Prolog, for instance, Horn formulas are called rules, and when they have no negative literals, so nothing on the left, they're called facts. And when they have no positive literals or literal, then they're called queries. And anti-equations, as I have already mentioned, are just particular cases of queries. Now, we can also think that not only we want to consider negation, but also we might want to consider disjunction. This has already been partially done in the literature, but what I'm illustrating here is a disjunction of things which are not equations, which are relational formulas. And if you work in a language of graphs, for instance, it's very common that you will have binary predicates, and you might want to talk about properties that involve those predicates, and those properties might contain disjunctions. Now, and about negative literals, you might, as I said, consider inequalities, or the negation of an equality, to be more clear, but you also might consider the negation of a relational formula. So in that respect, there are quite a few applications that we could have in mind when generalizing the set of equations. And one, I'm going to give examples about this, but the first obvious one is that, as we all know, any class of equations has a trivial model in which only there's a single object in the domain. What if you want to have non-trivial models? You want to guarantee that your models are non-trivial. You want to guarantee that 0 is different from 1, for instance, consistency. And I have already mentioned the constraint satisfaction problems over finite structures. They're often in the format of disjunctions. Graph coloring problems, they often say about this certain properties of adjacent nodes in a graph, and you want to say that, for instance, they cannot have the same color, and this is a negative thing to say about relational formulas. And as I have already mentioned, database querying often has a form of Horn sentences, in particular cases of Horn sentences. Okay, so let me give you some examples then. To start with a very non-exotic example, this is from mathematics. When you think about fields, you have a certain kind of structure in which you have that multiplication distributing over addition, if you want to read these symbols like this. And both these binary symbols are commutative and associative. You have an identity element. You have both for plus and for times, but you also have things like this. Any definition in any mathematics book about fields contains this assertion that 0 is different from 1, which is not an equation. It's a negation of an equation. Very simple one containing two constants, and perhaps we want to delete them, but let's see what happens if we consider the other axioms. So there's another one that says that there is there is a way of inverting according to addition, a certain element. And there is one which says that every null element can be inverted. Okay, so that is one which, if you write in terms of disjunction, will have two positive literals in a disjunction. Okay, and that you cannot write in the language of equations or conditional equations. Okay, so what if we want to produce a version of Birkhoff's theorem that would cover the class of fields, which are a very important class of structures? Well, then we'll have some trouble. The first trouble we can point out is that the class is not closed under homomorphic images, because you can just throw everything into the same object through a homomorphism, but you have the axiom that says that there are at least two different objects. So one element algebras are ruled out because they are the homomorphic image of any algebra, the type of field. Also, the product of two fields, if you take the pair 1, 0, the pair 0, 1, you do the product, the result is 0, 0. Yet, no field has 0 divisors. So you can also not guarantee that the product is going to be a field. At most, you can guarantee that the product is going to be a ring. And finally, also the proof of the Birkhoff's theorem uses free algebras. I didn't talk about the proof, but I'm saying now. And there is no free field. So you have troubles coming from all sides in trying to generalize that theorem. Now, what should we do? Well, I'm going to show some possibilities of generalizations from now on. And the first one is one which will take into account positive disjunctions and anti-equations of equality-based assertions. So in this part of the talk, I'm going to talk about languages that contain equality, but no relational symbols. And I'll talk about some generalizations of Birkhoff's results, which concern equality. Now, the first one, as you see, the theorem has the same format as before. Now, instead of talking about axiomatization through a class of equations on equality-based conjunctions, which are the equations, actually, now I allow also disjunctions. So I say that, imagine that your theory, rings, fields, whatever, new theory we're thinking about now, has two collections of expressions. The first collection contains only equality-based positive disjunctions, in particular could be a disjunction with only one object, which would be an equation. And the other class contains only anti-equations. So what do I mean by an anti-equation? It's just a universal formula saying that objects on the left and on the right are always different, instead of saying that they're always equal. And the second part of the theorem says that, well, there is a set of operations under which this kind of structures is closed, and there are three operations here. The second one you already know is subalgebras. The third one is not direct products, but ultraproducts. And the first one is a way of interpolating in between two structures from the class. Here's a definition. So when I'm applying this operation to a certain class of structures, what I have is a closure under the following operation, in which if you take the first structure and produce a surjection into another structure, and that other structure can be embedded through a homomorphism into the second structure from the beginning. So if for whichever A and B, I can find a way of factoring it through this certain C, then this C should also belong to the class of structures. So it's another way of closing under a certain C that interpolates A and B. So this theorem is very similar to Birkhoff's theorem, and it applies to other things, as I will illustrate in what follows. But just before the illustration, I just wanted to mention the reason why we're using ultraproducts. This was not discovered by us. It's very simple. It's because to preserve disjunctions, and I have now positive disjunctions, I cannot just stay with the direct products, but I need prime filter, and then the positive disjunctions are not necessarily preserved under reduced products. So I need the prime filters, I mean the ultra filters. Now this is going to come back in the future when I talk about all the kinds of disjunctions. It will be very common when disjunctions are involved that ultra products will take the place of direct products. Now, just for an example, if I want now not to work on rings, but I want my rings to be non-trivial, so I just write here the axioms of rings, and I write at the end something that fields have, but rings do not, which is saying that, well, there are these two objects, the two identity elements are different. Now I can write this because this is a disjunction, and it is an anti-equation. Okay, so it falls into the previous result. And the difference is that here there is no multiplicative inverse, like in fields, or multiplication not necessarily commutative, as you know. And the other properties are well known, like there are abelian groups under addition, monoids under multiplication, and multiplication distributes over addition. So the interesting thing is that now I can actually add this, which was not an equation, and study this new class of structures, non-trivial rings. Now, you might think this is not much, so let's go a little bit beyond that. Now, instead of having the disjunction of equations, now I have equations. And now on the other set, where I had anti-equations, I'm now collecting elementary anti-equations. And by elementary, I just mean that they are first order, in the sense of having being written in terms of conjunction, disjunction, finitary quantifications, the usual language of first order logic. And now I have the same two operations that I had before, but instead of ultra products, I have to use reduced products here. So the ultra products are more than what we need, and also because I have elementary anti-equations, I can work only with reduced products. Now, example. This is an example which is in the literature for a long time. You have De Morgan lattices, which have the usual De Morgan rules that you might expect. But you demand these lattices to be non-idempotent, and this is written in terms of saying that every element is different from its negation. This has been studied by a number of people, and they're also known as intentionally complemented distributive lattices, and they were introduced actually by Moisil in 1935. Now, in this case, we have identified that not only the set of operations under which these kind of structures are closed, but we localize them inside a bigger class of structures which have the same property of being closed under those structures, those operations. Now, for a parenthesis, that as we have already talked about, first of the logic, it's interesting to consider what would happen if we wanted our structures to be axiomatizable in the language of first order logic. And there is an intermediate result that I would like to show here, which is uses the concept of literal compactness, actually a weak version of that concept, which is just saying that if every set of literals finitely satisfiable is also satisfiable. So you see compactness there, obviously. And the proposition that we can prove using those first two operations, so the one of interpolation and the one of subalgebra, is that a class of a structure, which is, if you take one single structure and close under subalgebras and this interpolation operation, we may say that it's first order axiomatizable if and only if it has this property. So it's you might think it's an exotic property, but it talks about something which is well known to us, which is first order axiomatizability of structures closed under the operations that we have already explained. Now, for a similar result by Keisler, again by 1965, he talks about first order sentence being preserved under proper reduced products, and he proved that it happens if and only if this preservation happens if and only if the sentence is logically equivalent to a Horn sentence, which takes us back to the beginning, Horn sentences. Now, let me clarify here that what I mean by proper, because I didn't explain before, it means that it's the proper filter when you do the reduced product. So this result is, it shows you a kind of intersection in between varieties and anti-varieties, because there, as we have seen before, when we had these two operations, we had axiomatizability with equations and anti-equations. Now, for a different set of examples in which the language is not equality-based, but actually equality-free, from now on, I'm going to write properties that involve relations which are not the equality. And see that we have similar results to Birkhoff also in that case. For instance, very simple relation. When is it that you say that relation is irreflexive? Well, when it respects the object's axiom, saying that no x sees itself through the relation R. Okay, so the next theorem says, well, okay, when you have universal negative literals without equality, like this one, then you can guarantee that they are, the class of structures is closed under these two operations, and vice versa. So which are these two operations? They're very simple. H minus 1 is closure under homomorphic pre-images, and what I call PD here is the dual direct products. And by this duality here, we just mean that whenever in the definition of reduced product or direct product, we use a universal quantifier, here we use an existential quantifier. Okay, can we do more? Well, before we had only universal negative literals. If I now want to add also to these negative literals the universal positive literals, then I have a modular result. For instance, I might say that my structure has as axioms irreflexivity for the relation S, but reflexivity for the relation R. What happens in that case? Well, then we can prove a result in which we have the previous result here, using the two operations that I just mentioned, and we have Birkhoff's result here. Birkhoff's result take into account the universal positive literals, in this case, not necessarily equality-based, and the other result takes into account the negative literals. So it's interesting that this is like you add the two results to get this one, and the proofs actually show how this addition happens. For yet another example, I wanted to consider now not just universal positive equations, but positive disjunctions, of which equations are particular cases. So this is a further generalization, and now I can talk about things like irreflexivity, but also about totality. Okay, so a relation such that any 2 points are such that one sees the other, or vice versa. What about that? That's very common. How can we talk about that? Well, this next result says that when you have a theory containing positive equality-free disjunctions and equality-free negative literals, then it's closed under these two properties, these two operations, and vice versa. The novelty here is just that we have the reduced product and we take the dual reduced product. So as you see, we are taking a lot of advantage of dualization because we're going from something to the negative version of that something. So again, the dual reduced product is just the usual version definition of reduced product, changing universal for existential. Now, to go back to Horn sentences, there was a definition proposed in literature by Carlos Areces, Verónica Becher, and Santiago Ferro 20 years ago about what they called D-Horn formulas, which sort of dualize Horn formulas. But we here consider an infinitary version of their definition. And we call a formula basic D-Horn if either it contains at most one positive equality-based literal, or all the equality-free literals are positive, and both these things happen, or they're duals. All equality-based literals are negative, and at most one equality-free is negative. Okay, so with that definition, and I'll give examples of those, we can define what's called a strict D-Horn sentences. As you look here, it probably looks very clear to you that this is the dual of Horn sentences, because instead of having conjunction on the left, I have a disjunction on the right. Okay, what can we prove about this? Well, that if you take a class of structures in a language without function symbols, and you close it under these two operations, this is axiomatized by the collection of all strict D-Horn sentences that hold in all the members at once. And moreover, if you want to consider a situation in which this class is first order axiomatizable, the solution is, it happens exactly when this closed set of algebras is elementary strict D-Horn in the usual sense of elementary. Okay, so let me just clarify that this operation here, h minus 1s, which looks like the pre-image, actually it's closure under strict homomorphisms. Okay, pre-image of these strict homomorphisms. Okay, now what can we do with that? A very simple corollary follows from that, is that a class of algebras is elementary, strict D-Horn, if and only if it's closed under those so-called strict homomorphic pre-images I have already mentioned, and under dual direct products. And moreover, is first order axiomatizable. So this is a very general characterization of the class of structures that these people have used before, have introduced in literature many years ago, in a generalized setting, and in something that looks like Birkhoff's characterization. So you're looking at what do you say, purely mathematical characterization of mathematical things, so syntactical objects, which are those covered by certain kinds of sentences. Now, just to give examples, for instance, this is it's a made-up example, but it's not uncommon, because what you have here as axioms is say that now that you have disjunctions, this is just like bottom. So this is just saying that the first axiom is irreflexivity, that you can now write in this language. You can write symmetry, and you can write things like, well, whenever x sees y, then z must be either ahead of x or of y. So every third object must be related to one of the first two. Remember that we have symmetry. So what if I want to study this kind of structures? Well, they fall into the class of things which have a strict D-Horn characterization, and they have those properties, and they obviously can be axiomatized because they are axiomatized here, but we now know that other things that look like them have the same properties of being closed under the same operations. Okay, I'm not taking you much longer into this here. I just wanted to mention one last thing in this section, which is axiomatizability by strict de-Horn sentences. Why is this interesting? Well, as before, Birkhoff's result was first generalized by going from varieties to quasi-varieties. Now, what if we're interested in de-Horn classes, so not just conditional equations by this, but these de-Horn sorts of objects, these dual Horn equations? Well, in that case, we can prove a result that says that, well, a class of algebras is elementary strict de-Horn if and only if it's closed under these two operations. Of course, you don't need to remember all those operations. You just need to notice that we're talking about a certain class of algebras and a certain class of operations on those algebras, and closure under those operations is giving us a new perspective on the class of algebras itself. Now, Maltsev's characterization theorem for quasi-varieties said something about the class containing a trivial algebra being closed under isomorphism, subalgebras, reduced products. And now we have something a little bit different, which is the theorem that follows. And it's the last theorem that I'm going to show. A class of structures without function symbols is such that 1 and 2 are equivalent. So 2 says that the class is axiomatizable by a collection of strict de-Horn sentences, those things we just talked about in the last 2 slides. 1 says that the kind of thing we're talking about here, the kind of closure that we are going to use to identify this axiomatizability is closure under dual direct products, strict homomorphic pre-images, and this object here that I called 0. 0 is just the dual direct product of an empty family of structures. So by definition, it's just a structure whose carrier contains a single object and a collection of empty relations. So all positive literals fail in 0. Okay, so Maltsev had to do something similar when he introduced the trivial algebra in his characterization of quasi-varieties, and we now have something that plays a role of that trivial algebra here, dualized into the 0. Okay, so by way of closure, I wanted to mention some interesting directions which I think deserve attention in the literature. First of all is that we started in a very bold intention of generalizing actually Birkhoff's theorem so that we would be able to basically take any sort of axiomatization with as general first order language as possible, and we failed. But we were able to get several classes, interesting classes, like those containing disjunctions, containing anti-equations, combination of those things. So many things which we couldn't talk about before, we can. But for instance, there are things which have not been covered. And some of them are actually can be easily found in computer science. One example is the class of undirected graphs, which is closed under this interpolation property that appeared in theorem 5. Okay, so, but it's not covered here because there is an example in the paper, symmetry of the interpolated structure fails. So if you close under this, it fails symmetry, and undirected graphs are obviously symmetrical for being undirected. So this class will not be closed under these operations, so we cannot apply theorem 5 to it, which was the most general theorem that I proved before. And other things that we cannot do, which are worth mentioning and are worth further investigation, in my opinion, is to look at, for instance, theorem 3, which is the one that concerned universal negative equality-free literals, such as the irreflexivity axiom. And remember that in that theorem, the corresponding operations were homomorphic pre-images and dual direct products. The problem here is that if you want to define an analogous of that result to take anti-equations into account on algebraic systems, the obvious definition of congruence that you need to prove the result fails transitivity. So it's not even an equivalence relation. So the the analogous of that theorem, we have to look for another operation, which would be the correct analog of dual direct products, and we don't have any idea of what that would be. Okay, so it's a challenge to find. I've shown many examples of success, but in some cases, it's still a challenge to find the right operations under which the class of structures is closed. And to end, I just wanted to put here a provocation, which is when we start doing mathematics, at least historically, we produce all these beautiful classes of algebras, and then we start as logicians looking at the languages and looking at what do they have in common, and then we try to find ways of characterizing them using the same language, say the language of equations, the language of conditional equations, and so on. But later on, once we have identified a certain language, we can start creating new structures, those that people have not thought before. And now, the results that I have presented here, actually, what they do are precisely this. They allow us to consider much more generous languages, which will, by their own turn, allow us to define much more generous classes of structures. So do they already exist? Maybe we have just to look for them and we will find them, for instance, as I have conjectured, in computer science, in constraint satisfaction problems, in coloring problems, and things like this, which mathematicians have failed to look because they were not interested in those kind of structures. But maybe, actually, what we are interested is in creating new structures. And now we have the language for that. Let's do it. Thank you very much for your attention.
Muito obrigado, João, pela apresentação. Bom, vamos iniciar agora um espaço para discussões, comentários, só para evitar problemas na comunicação. Peço que vocês usem o chat para se manifestar que querem fazer perguntas ou algum comentário para a gente organizar uma fila. Cassiano, primeiro inscrito, por favor. Cassiano, você pode falar se preferir. Pode habilitar o microfone nesse momento. Bom, eu acho que o Cassiano está tendo algum problema com o microfone. Enquanto isso, Valéria, você quer fazer a sua pergunta?
Oi, quero sim. Bom dia a todo mundo. Eu queria saber o que você sabe, João Marcos, sobre a situação quando a gente está falando de hiding algebras, quasi-varieties, eu acho que elas são. Porque eu acho que esse é o tipo de extensão que eu estou mais interessada, né? Assim, eu tenho dois interesses tradicionais. Um, ver essas coisas quando são sistemas construtivos, e algumas dessas coisas não funcionam no momento, né? Mas a outra coisa seria tentar pensar nesses sistemas quando a gente está pensando em coisas mais que nem linear logic. Aliás, eu devia perguntar isso, se vocês querem pergunta em português ou em inglês, que eu fico aqui misturando as coisas.
Fica à vontade.
Como você preferir, Valéria.
Obrigada. Mas você entendeu a minha pergunta, João Marcos?
Entendi. Quando você perguntou que tipo de resultados a gente tem para álgebra de Heyting, elas são bem pouco exóticas do ponto de vista da apresentação que eu fiz aqui, né? A gente consegue cobrir, tradicionalmente, o resultado de Birkhoff cobre as variedades, o resultado do Maltsev cobre as quasi-variedades. Então, ali a gente não tem muita novidade. Mas se a gente quiser acrescentar coisas, por exemplo, fazer uma expansão dessas álgebras para poder acrescentar novas operações, e essas novas operações precisarem, digamos, de disjunções para serem escritas, vai ser muito natural tentar aplicar uma extensão dos resultados, né? Tentar ir além dos resultados que a gente tem aqui agora, que conseguem falar de disjunções. Ou se eu precisar de falar que as álgebras são não triviais, por exemplo, que a gente não consegue falar usando equações, né?
Mas a gente não, assim, quer dizer, me lembra do que a gente sabe de verdade. A gente sabe que tem um resultado do Malsev funciona para Writing álgebras, para álgebra de Writing?
Sim.
E mas a gente não tem eu acho que a gente não tem nenhuma maneira de pensar num resultado do Birkhoff para coisas que sejam lineares, contando o número de vezes que as coisas são usadas, né? Ou tem?
Ok, já vi onde é que você está.
São as duas extensões que eu quero, né? Uma para coisa construtiva, outra para coisa linear.
Essa outra coisa linear me parece que cabe bem dentro do que eu estava preocupado aqui, ou em princípio, né? Quando você fala em contar, a gente está sempre dizendo ou é isso, ou é aquilo, ou é aquilo outro. E não é nenhuma coisa a mais do que uma dessas três. Dizer que é igual a 3 é dizer que é no mínimo 3 e no máximo 3. Esse tipo de sentença a gente consegue escrever agora. Então, se a gente tiver que falar de estruturas finitas, essas caracterizações de finitude usando disjunções, a gente consegue falar agora, usando essa linguagem. Isso sim. Eu não sei se no caso das estruturas lineares que você está interessada, se elas vão ser sempre finitas para um tamanho finito conhecido de antemão. Porque se ele não for, a gente vai ter um número infinito de axiomas possíveis, né? E vai ter que falar da disjunção deles. Isso pode ser um problema, mas pode também não ser. Na linguagem que a gente trabalha no nosso paper, a gente usa linguagens infinitárias e permite escrever sentenças infinitamente longas. Então, em princípio, eu teria que ver qual é a propriedade que você tem em mente, mas, em princípio, pode ser que a gente consiga, já nessas linguagens, ou em uma dessas linguagens, com disjunções de equações, ou de equality-based, universal equality-based positive disjunctions, cobrir esses casos que você está interessado no caso linear.
Certo. Muito interessante. Muito obrigada.
Obrigado a você.
Bom, só repassando a pergunta do Cassiano, ele pergunta o que a citação do Wittgenstein no final tem a ver com a apresentação e pede para você explicitar um pouco mais a questão dos limites da linguagem.
Perfeito. Obrigado, Cassiano. A última coisa que eu falei, antes de terminar aqui, deixa eu voltar aqui. A última coisa que eu mencionei, que eu falei que era uma provocação, tem justamente a ver com a citação do Wittgenstein sobre o limite da minha linguagem, esse é o limite do meu mundo, quando eu disse que a gente começava do mundo, né, os matemáticos começavam assim, das estruturas com que eles já conheciam e tentavam capturar essas estruturas usando certas expressões lógicas. Então, eventualmente, se eu consigo descrever uma estrutura usando, digamos, equações condicionais, e mais tarde eu descubro que tem uma outra forma de descrever, que não precisa de equações condicionais, que consegue trabalhar só com equações, a gente acabou de passar de uma estrutura que é uma quasi-variedade, uma classe de estruturas que é uma quasi-variedade, para uma classe que é uma variedade. Bom, quando os matemáticos demonstraram esses primeiros resultados sobre a forma de caracterizar as expressões, usando um certo tipo de linguagem, nesse caso, a linguagem das equações condicionais, por um lado. E do outro lado, os objetos que eles já conheciam no mundo lá fora, grupos, anéis, etc., né? Qualquer outra estrutura algébrica conhecida ou exótica que possa ser escrita em termos de equações condicionais, esses resultados mostraram que muito do que a gente sabe sobre essas estruturas é espelhado, de uma certa maneira, na escolha de uma linguagem muito específica e muito restrita que usa expressões que são cláusulas de Horn, são sentenças de Horn. E aí, uma vez que a gente já tenha feito isso, a gente pode agora, que está vivendo dentro da lógica, pensar ao contrário. E se eu, dentro da lógica, conseguir pensar em expressões um pouco mais gerais, ou diferentes daquelas expressões, equações condicionais, ou expressões de Horn, consegui dualizá-las, consegui falar de disjunções, de negações, etc. E agora defini uma nova estrutura através das equações, não através da minha intuição sobre o mundo, mas através da linguagem. E, a partir dessa definição, eu falo, olha, eu acredito que essas equações generalizadas descrevem exatamente o tipo de objeto no qual eu estou interessado. Bom, isso é uma maneira usual hoje de criar objetos. A gente cria formalmente, dizendo quais são as propriedades que a gente gostaria que eles tivessem. Mas não é porque a gente já está generalizando alguma coisa, como, por exemplo, grupos generalizaram os números inteiros. É porque a gente está tentando capturar com a linguagem a nossa intuição sobre certas propriedades que deveriam ser satisfeitas. E agora a gente quer verificar quais são as estruturas que satisfazem essas propriedades. Então a gente passou no sentido contrário agora. A gente expandiu a nossa linguagem e com isso, digo eu, a gente expandiu o nosso mundo. A gente consegue falar de mais coisas. E coisas talvez que a gente não teria pensado em falar antes, porque a gente nem desconfiava que a gente teria linguagem para falar delas. Obrigado a você.
Obrigado, João. Alguma pergunta a mais? Valéria?
Oi, desculpe, desculpe a demora para achar o microfone de novo. A outra pergunta, João, é sobre essa história de interpolação. Você está falando que os seus homomorfismos, em vez de serem somente H, agora eles são um par, H e H-1, né? A pergunta é se esses pares, H e H-1, tem a ver, se isso tem a ver com a interpolação do Craig.
Eu chamei, obrigado pela pergunta, eu chamei de interpolação a partir dessa intuição. Eu não sei até que ponto que isso poderia ser pensado como uma generalização da interpolação de Craig. Mas é muito parecido, né? A interpolação do Craig tem duas versões, a versão sintática e a versão do mundo, né, lá fora, das estruturas que entram no meio, né? Essa versão aqui nossa é semântica, né? A gente está falando de operações. E essa é uma operação que tem um símbolo esquisito para poder escrever, né? Que é H-1, mas é para poder lembrar do que está acontecendo. O que está acontecendo é que eu tenho dois objetos lá dentro da minha classe de álgebras e toda vez que eu puder comprimir o primeiro objeto de tal maneira que eu consiga fazer um embedding dessa compressão dentro do segundo objeto, então esse cara do meio do caminho, esse cara que é o primeiro objeto comprimido, também devia estar lá dentro.
Parece muito com Craig, né?
Mas eu não tenho certeza agora, não posso dizer agora que é a mesma intuição, mas é um objeto sendo interpolado, claramente, né? Agora é um objeto semântico, uma álgebra sendo interpolada entre outras duas.
Ok, obrigada também.
Bom, temos uma pergunta do Petrúcio. Petrúcio, você quer falar?
Olá, Petrúcio.
Eu acho que ele está tendo algum problema com o microfone.
Estou vendo a pergunta aqui por escrito, eu posso repetir, se não for isso, ele grita. Ele escreveu que, pelo que entendi, os resultados apresentados são restritos à lógica de primeira ordem, infinitária ou não. Existe algum estudo desse tipo para lógicas de ordem superior? E se isso faria sentido? A pergunta é difícil. Obrigado pela pergunta difícil. De uma certa maneira, eu posso dizer, eu talvez deixei isso um pouco escondido na apresentação, a gente já considera uma lógica além da lógica de primeira ordem, infinitária ou não, porque, para facilitar os nossos resultados, e para não ter que estender, e para não ter que restringi-los só à linguagem de primeira ordem, a gente assumiu desde o começo que tinha uma linguagem, vamos dizer, não vou nem dizer que é L ômega, é mais do que isso, é L infinito, infinito. Eu posso ter expressões de qualquer tamanho, posso ter codificações de qualquer tamanho, para facilitar as demonstrações dos teoremas. é possível restringir as demonstrações para linguagens mais usuais. Tá? A gente não fez isso no paper. Eu estou dizendo isso para dizer que, como a gente tem essa linguagem muito generosa, então, de certa maneira, eu poderia dizer que a gente já cobre parte do que a lógica de ordem superior cobre. Parte, né? Não cobre a possibilidade de quantificar sobre outros objetos que não sejam aqueles que fazem parte do domínio. Né? Mas eu posso fazer quantificações de ordem superior, no certo sentido, posso fazer quantificações arbitrariamente complexas, e já que eu também não coloquei nenhuma restrição sobre o que está no meu domínio, eu posso até simular algumas versões de lógica de ordem superior. Isso não é a resposta para a sua pergunta, mas é para dizer que a gente já está indo um pouco além da lógica de primeira ordem. Com relação à pergunta, de fato, se isso faria sentido, eu acredito que sim, mas eu não tenho a menor ideia de como fazer. Simplesmente porque a maneira como nós demonstramos esses resultados, como alunos que somos de teoria dos modelos e de álgebra universal, e longe de sermos especialistas no assunto, foi simplesmente abrindo o livro do Hodges, abrindo os livros clássicos e vendo o que a gente precisava modificar dos resultados clássicos, quais eram os objetos que a gente precisava encontrar para imitar aqueles resultados. E o que é que se encontra no livro clássico de teoria de modelos? Lógica de primeira ordem. Então, num certo sentido, porque isso é um estudo modelo teórico, e a teoria dos modelos pode ser dita como, pode, de certa maneira, ser dita como sendo o estudo da lógica de primeira ordem, num certo sentido, porque quando vai além daquilo, os resultados quase todos vão se perdendo, né? Completude, Lindstrom, etc., todos começam a se perder. Então, nesse sentido, eu não tenho a menor ideia de por onde começar para procurar por uma generalização desse estudo para lógicas de ordem superior na linguagem ampla que elas podem ter, na linguagem mais ampla possível da lógica de ordem superior. Ou seja, eu não sei como fazer.
Mais alguma pergunta? Bom, aparentemente não. Se alguém tiver alguma... Petrúcio disse que está esclarecido e agradece.
Eu agradeço.
Então, bom, se não temos mais perguntas, queria te agradecer mais uma vez, João, agradecer a todos que estão presentes. Lembrando que essa sessão foi gravada e vai ser disponibilizada no recém-criado YouTube da Sociedade Brasileira de Lógica. Se alguém que falou tiver qualquer problema com isso, por favor, entre em contato o quanto antes, preferencialmente se manifeste agora. Aproveitando o momento para fazer divulgação, então, na próxima semana, dia 16, a professora Valéria de Paiva vai fazer a apresentação com o título Between Broken and Hard Place, Structural and Distributional Meaning Representations. Vai ser também numa quinta-feira, nesse mesmo horário. Espero contar com a presença de todos vocês. Muito obrigado, pessoal. Mantenham-se a salvo. Fiquem em casa, se possível.
Eu só queria agradecer também a presença de todos. Foi um experimento bastante interessante e novo, e eu desejo longa vida a essa iniciativa e parabenizo mais uma vez a Sociedade Brasileira de Lógica por estar organizando isso e as pessoas todas que vieram aqui assistir por terem dado esse apoio. Obrigado.
Obrigado, João.